finally, it is my great pleasure to introduce our first speaker for this year's World Space Week. Dr. Ben Dreyer is a Space Instrumentational Research Fellow in the Centre for Electronic Instrumentation in the School of Physical Sciences here at the Open University. He has worked on a number of ESA missions, and we will hear hopefully about 2 of those missions today. Ben also chairs the modules S818, which is Space Science, and is an associate lecturer on SM123, Physics in Space, and S217, Physics from Flassel to Taunton. So it gives me great pleasure to introduce Dr. Ben Dreyer, who will be talking about Image in Space, the JUICE and Euclid missions.
Thank you. So yes, welcome everyone. I think today's going to be a bit of a whistle-stop tour because I could talk for about 2 hours on any of these topics really, but I've been asked to talk about all of them in 40 minutes. So we'll see how far we get. It'll all be talking about the science that's going on and the work that we do here at the Open University. A little bit about me first. Alice, thank you for the introduction. That was fantastic. Here's a picture of me and the 5 things I care about the most in the world. I'm a researcher at the Open University. About half of my work is research, half is teaching. It's great to see, I saw in the participant list some of the S217 students from last night who are just starting their module. And anyone who's had, you know, interactions with me on the modules, welcome. It's really good to see you here. Welcome to members of the public who may be joining. I see there's a few associate lecturers joining as well. And I hope this is an enjoyable session that everyone can get something out of. My research work, I work at the Centre for Electronic Imaging, so that's this logo here. This is a research group at the Open University that concentrates on, it's starting to branch out more, but it's about 20 of us who concentrate on radiation damage to cameras that go on space missions pretty much. And we work very closely with this company, Teledyne E2V. It was formerly E2V, the company in Chelmsford in Essex in the UK. They were recently bought by Teledyne, US company, and they manufacture these space sensors that go on a majority of European Space Agency missions. And as part of our partnership, we get to work closely with those sensors to do our research, and we get access to very expensive sensors, flight grade sensors that would cost a lot of money. And in return, they get the benefits of our research to improve their devices and to help their customers make decisions about sensors. In each section, I'll go over the mission, what it's going to do in terms of science, what the instrumentation on the mission looks like, and where the OU is involved. I'll do that for JUICE and Euclid, and then at the end, we'll talk a little bit about radiation damage in a bit more detail, because it's one of the most important things to consider if you want to launch something into space. So the first mission I'm going to talk about is JUICE. So I guess first I should say we've got this space mission here, which is Gaia. That was, you know, you always hold a special place in your heart for your first space mission, and that was mine. So Gaia's been up since 2013, and I worked on the radiation damage characterization for it before that time, and it's been in space operating for a decade now, when the mission life was predicted to be about 5 years. So it's extended its life beyond what we predicted, and that's partly down to the work that we do here to get as much science as possible out of these space missions and improve the return on investment for space agencies. So JUICE, you will have heard about it. It was launched this year on the 14th of April from Kourou. It stands for the Jupiter Icy Moon Explorer, and the main goal of the mission is to investigate the moons, specifically the large icy moons of Jupiter, because there's evidence that there may well be either habitability there or even life. It's an L1 mission, so ESA have these kind of mission calls. L stands for large, so this is the first L1 mission in the Horizon program. And the Horizon program has these letters and numbers. We'll go on to Euclid, which is an M2, so it's the second chosen medium class mission. And that's what it looks like on the right there, these very distinctive cross solar panels. And that was launched successfully on the 14th of April, and the OU got some good media coverage about the work that we've done. So if you were to look at Jupiter with your telescope, you'd get an image something like this. It's very blurry because you're looking through the Earth's atmosphere, and that, like looking through water, the more atmosphere you go through, the more the light rays are deflected by molecules in the atmosphere. And so you always end up with a blurry image. You can't avoid that from the ground without some very sophisticated technology. And there's, some of the world leading observatories are doing their best to counteract this effect. So what do you do if you want to get, this really is kind of the best kind of shot of Jupiter you can get from a telescope. What do you do if you want to investigate more about this planet? Well, the next step, which we did a few decades ago, is to send a telescope into space, get it out of the atmosphere, and we don't get this blurriness. So here's a picture of Jupiter taken by Hubble. And you already see a complete change in how we can understand what's going on the planet just from this image, right? You can see that it's clearly looks like it's got liquid or gas swirling around pretty much all over the surface of the planet. It's clearly not a rocky planet, at least from what we can see from the outside. You can see more details of kind of the turbulence and the weather that's going on the planet, and you can start to make some more scientific observations about how Jupiter works and what kind of processes are going on in the atmosphere. That's great, but what if, what would we see if we went even closer and got some more high resolution images? Well, we've done it. So the Juno space mission went up some time ago. It's a NASA mission, and it brought back these completely different, stunning images of the dynamics of Jupiter's atmosphere. There are many more of these kinds of images online that were taken by Juno. It's well worth having a look. There's lots of different effects going on Jupiter, depending on if you're at the equator or at the poles. It's well worth looking at these, but you can start seeing this kind of fine-grained, like we have on Earth, satellite images of the clouds and things like that. And this allows scientists to start really understanding what's going on in the atmosphere of Jupiter. And there are lots of open questions about planets other than Earth, though there are lots of open questions about Earth, but the other planets, they're relatively unexplored. And the processes that go on there are very different to the processes that we see on Earth. So it's very important that we understand these different worlds, because that will inform our understanding of these processes and how we might make more accurate models for weather on Earth, or we might make accurate models for possibly inhabiting another planet at some point in the future. But JUICE is not only concerned with Jupiter, it certainly will be observing Jupiter as it approaches, but it's more concerned with the icy moons of Jupiter. Now, Jupiter's not concentrating on Io, the leftmost one on the image here, but it is going to concentrate and visit Europa, Callisto, and Ganymede. And this really is a kind of collage of what kind of terrain exists on these moons, or why they might be interesting to us. Io is one of the innermost moons, and as a consequence of that, it's very strongly affected by Jupiter's gravity, Jupiter being the most massive planet by far. And so because it's so close and Jupiter's so massive, the front of the planet feels more gravity, the front of the moon feels more gravity than the rear of the moon. And so as it rotates, it gets squished in different directions in the same way that the moon affects our oceans and gives us tides on Earth. And that makes Io extremely volcanic. So Io is one of the main sources of radiation around Jupiter. And it's the volcanoes that, because the crust is constantly being compressed and stretched, these rifts in the moon open up in the form of volcanoes. And those volcanoes, because the moon has fairly low gravity, those volcanoes are spewing material out into the orbit around around Jupiter. So Jupiter actually has rings. We don't really think of it as a planet with rings, but it has very thin, dusty rings. And those rings are mostly populated from volcanic activity on the moons. But moving on to what JUICE is actually going to be studying, which are these three other large moons. You can see in the close-up terrain images at the bottom here, they're actually very different looking in terms of their characteristics. Europa is kind of covered in a sheet of ice, and what you can tell just looking at the bottom image here is, compared to Callisto and Ganymede, it's got relatively few craters on the surface, and that's a bit of a puzzle, because you would expect it to be hit by meteorites as much as any other moon around Jupiter. So what we think is happening here, you see these cracks in the surface. So what we think is happening is you've got a surface of ice, frozen something. I'm not sure if it's water ice, but frozen liquid. And you have these cracks in the surface, and those cracks are constantly, the liquid underneath is coming up through these cracks, and this renews the surface. So when a meteorite hits, it forms a crater for a small amount of time, but it's very quickly swept away by this renewal, this flow of material from the subsurface up onto the surface of the moon. So because it has no meteorites, we know that this is probably a fairly young surface that we're seeing, and the material there has been processed on the surface. If we compare that to Callisto, it's really a completely different moon. It's more like our moon, I would say. There's no kind of renewal of material there on the surface, and instead you see the weathering due to it being in space for billions of years. So you see a surface that's actually much older, and has different types of material than we see on some of the other moons. And Ganymede kind of sits halfway in between, and that Ganymede's interesting for its own reasons, which I'll go into in a minute. So the main thing that the public are interested in, and scientists are interested in, is really the habitability of these moons. Ganymede and Europa, those two moons, there's evidence from previous missions that there's a liquid subsurface underneath the crust, and we all know that liquid water is a very important component of life. The reason why there's liquid under the surface is, again, if you think about that squashing that I talked about with Io, it's a bit less pronounced on these moons, but this squashing happens. And if you think of a squash ball, if you've ever held a squash ball and you've squeezed it a few times, it heats up pretty quickly. So it's actually that squashing of the moon that gives it an internal heat, that friction of the rock as it gets pressed by gravity. And that allows these moons under the surface, although the surface is very cold and exposed to space, underneath that subsurface, that heat can be retained, and actually it can reach temperatures that might be habitable for life. They also have, there's also radioisotopes in there, and that also contributes to the heating. The decay of these isotopes puts energy into the environment, and that heats up the subsurface, which allows the liquid to be there. Something else that's really interesting, and this is what I was talking about before, Ganymede has a magnetic field, which might not initially seem surprising, but I think it's one of the only moons that we know of that has its own magnetic field. And why is that important? Well, one of the only reasons that we have life on Earth is because Earth has a magnetic field that protects us from space radiation. What happens when you don't have a magnetic field is particles from space can hit the surface of the planet, and they give energy to molecules. So when you're building complex molecules that are necessary for life, like amino acids, etc., they get very quickly broken up into their constituent parts before life has a chance to form. So one of the theories is that our magnetic field has allowed Earth to be habitable for life. And so there are instruments on JUICE that will measure the magnetic field of Ganymede to understand it better and where it comes from. There's also instruments on JUICE that will look for biosignatures, the elements that we know are important for life: carbon, oxygen, water. The mission will be able to scan for those kinds of elements. It's not really capable of finding life, but it can find all the things that life needs. And if many of those signs are present, then we can follow up with another mission that may well be able to look for activity of life on the surface. And I think it's great if we understand that our gas giant, one of our gas giants, has habitable environments around it. But I think actually it has more far-reaching implications if we do detect that, because most of the planets that we see around other suns currently, the ones that we can detect, are gas giants as well. So if we're able to find habitability or life, I think there are wide-reaching implications for understanding our place in the universe and how common life is in our galaxy. So if we get that kind of confirmation, we may, but we can't find life, maybe it's a good idea to start looking at gas giants around other stars, see if we can detect signs of life from a distance. And like I say here, maybe Earth's not special in terms of having life. Maybe it's the only place that we've been able to look hard enough to find it. There are lots of other questions about Jupiter, and I realize I'm probably talking for too long about Jupiter to fit everything in this talk. We talked about Jupiter's rings. They're not well studied, but it has thin, dusty rings that may well contribute to processes on the surface of Jupiter. And there's always this, the Jupiter it's just so massive, and there are so many interesting atmospheric processes going on there. So JUICE is going to take more detailed measurements than we've taken before of what exactly is going on in Jupiter as well. And Jupiter also has these very strong magnetic fields, which kind of traps and accelerates high energy electrons. So it's actually a very harsh radiation environment. And so we need to understand how that electron population might be interacting with the moons and interacting with the planet in order to understand habitability as well. This is the mission. I won't and can't go into detail on many of these instruments, but it's an L-class mission. It's a large mission, so it has a full suite of laboratories and instruments on board. Some of these are measuring magnetic fields, some of these are measuring geophysics, some of these are measuring taking high resolution images. There's lots and lots. I think there's about 10 to 12 instruments on board, depending how you count. But the one that we worked on at the Open University is JANUS. So I'll just give a quick introduction of the work that we've done on that. JANUS is an awful Latin acronym, but if you translate it, it's actually quite nice. So it stands for Jovis Amorum ac Naturam Undique Scrutator, which translates roughly to comprehensive observation of Jupiter, his love affairs and descendants, which obviously links into the mythology of Jupiter from Greek and Roman mythology, the moons being named after his relationships. What we do, so on the right here, you see the sensor that's being used on board JANUS, the instrument, and this is the main high resolution imaging camera on board JUICE. So all of the beautiful pictures that we're going to get back will be coming from the camera that we worked on here at the OU. It's the main scientific imager on board. And images are data. It's not just the camera. Images give you so much information about what's going on, about the geology, the atmosphere, etc. They are measurements. One of the challenges of Jupiter, as I talked about, is this very high energy electron environment, and we'll talk a bit at the end about how these types of particles can affect the data that we're taking on JUICE. It's kind of a landmark for space science in general, because it's one of the first large camera devices using CMOS technology. So there are two technologies. I don't want to go into it in this. It will take too long to explain. But CMOS is kind of like the technology you have in your mobile phone. And in general, it's been very good for consumer use, but hasn't been used in space as much. So this is one of the first ones where this technology has been pushed to a level where it can now produce really good scientific information in space. I just want to kind of give you an update on where it is, and then we'll move on to Euclid. So this is always fascinating to me, how they plan how JUICE is going to get to Jupiter. So it was launched earlier this year, but it's actually got an extremely complicated way to get there. So it launches from Earth. Here we've got Earth going around the center. It comes by and swings by the Earth a second time, and that gives it an extra energy. And it does the same to Venus. So it actually goes into the solar system and gets pulled by Venus's gravity. Does another swing by of Earth and then a swing by of Mars. So each time it swings by a planet, it's sucking gravitational energy out of the planet and adding to the spacecraft's kinetic energy. And in this way, we can reduce the fuel that we need to pack on board. It swings by the Earth again, and then off it goes to rendezvous with Jupiter. So in total, it does 5 or 6 swing bys of different planets. And this is why when it launched, it only had a 1-second launch window each day of that week it was due to launch. And they just weren't confident on the first day. So the launch was delayed by a day, and they had to wait for the next 1-second window for launch. And then it rendezvous with Jupiter and enters orbit around Jupiter. So that'll take 8 years. There are challenges with sending a thing into space for 8 years, which we'll talk about a bit later. So can I just move to the next slide now? Is it going to work for me? Yes, fantastic. Oh, okay. So here's just a little bit of information about how much radiation it might get. So this is from Gaia, and Gaia measured its radiation every day in space. This is the x-axis here is in revolutions. So all you need to know is that 1,500 revolutions here is about a year. So then 3,000 is another year in space. And this is a measure on the left of amount of radiation damage, basically, to the camera. And you can see the steady build-up. So Gaia is in orbit around Earth. You can see the steady build-up over time of radiation. And after 2 years, it's actually quite significant. So if you imagine putting a spacecraft into space for 8 years, that gives even more challenges to fighting radiation damage, which I'll show you later. Euclid. So I realize I need to speed up a little bit, and that's going to be challenging when I need to explain to you what dark matter and dark energy are, but we'll do our best. So as I said, it was the M2 mission. So this is the second medium class mission from ESA's Horizon program, and it's really concentrated on mapping the dark universe. There's only 2 instruments on board. They're large camera type instruments. There's the VIS, the visible imager, and NISP, which is the near infrared spectrometer. And it was launched on the 1st of July from Cape Canaveral. We had a few people go out there and watch the launch. So what is dark matter? What is dark energy? This is the normal matter here, that small slice of the pie. The pie represents all the energy in the universe. And normal matter is matter that we can see. We know that in solar systems, the vast majority of the mass is in the sun, is glowing. And so when we add up all the mass that we can see, all the mass in the stars that we see in the universe, and we measure the effects of the mass, we find a drastic disparity in that there seems to be much more mass existing than the mass that's glowing. And this is a huge problem for cosmology, because if we can only see and measure 5% of the mass in the universe, where's the rest of it gone? And that the effects of the mass that we can't see must be dominating the physics and the cosmology that's going on in our universe. So Euclid is going to be the first mission that really delves deep into understanding the missing 95% of energy in our universe. So about just under 70% is dark energy. Dark energy is, if you measure very far away galaxies, they are accelerating away from us. So it's not just like the Big Bang happened and everything moved away at one speed, like you would expect a normal explosion. In fact, the things far away from us are expanding away from us faster and faster every day. So there's an energy there that is pushing the universe outwards, whereas normally if it was just matter, we'd expect it to all collapse inwards. So there's some energy there that we don't see, we don't understand, that's pushing the universe apart. And that's what we term dark energy, just dark because we just don't know what it is, where it comes from. And then there's about 25%, which is this dark matter. And that's mostly what I'm going to talk about today, because that's what my instrument is looking to measure. But dark matter is matter with mass, but we don't see it. There's no light coming from this matter. So the sum, we don't really know what it is. Is it just, is it mostly particles that are flying about in free space? It's matter that doesn't interact with light really, or absorb or emit light. And we just don't know how that much mass exists and has effect on what we measure without being able to see it. So Euclid is really the first mission that's trying to understand the distribution of this dark matter in our galaxy and how it affects our understanding of our universe and cosmology. So there's a few slides here just kind of giving you a more visual example of dark matter and how it affects our understanding of the universe. So the first one here is two side-by-side galaxies. These are simulations from the Eastern Observatory, ESO. And on the right here, you see, on the left here is what we measure galaxies to rotate like. But on the right is a simulation of a galaxy with just the visible matter that we can measure. And you see a drastic difference in what we measure and what we expect from theory. And this one explanation for this could be that there's matter that we don't see that is more kind of uniformly distributed throughout the galaxy, that's accelerating, that's adding gravity in there that accelerates the stars, makes it rotate more in line with what we measure. So that's where kind of the foundation of dark matter theory came from. Euclid is going to measure the distribution of this dark matter. It's really because does it behave like normal matter? So here on the right you see basically a universe simulation. So from the CLUES project, there's 1 billion particles here, which is at the beginning fairly evenly distributed throughout the cube, and then they let that matter interact through gravity over billions of years. And what you see is something that's very uniform to begin with. Any very slight variations in that uniformity, the uniformity comes from the Big Bang. Any slight variations that are there over billions of years get exaggerated drastically, and you end up with a universe that has these filaments of matter in it, because anywhere where there's a slight higher density than other areas, that gravity is going to be stronger and it's going to pull everything together. And this is what we see with matter in our universe, and Euclid's trying to see if we observe the same with dark matter. This is an actual measurement of matter in our galaxy, in our universe. And what you see on the top here is, on the left is very close to us, and on the right is very far away from us. And what that means, because light has a speed limit, so light takes time to reach us. So on the left is actually the old universe, because we're seeing light that's coming very recently to us. So light that's come from space that has had billions of years to interact under this gravity. Whereas on the very far measurement on the right here, you see a more uniform distribution, because that light has taken a long time to get to us. And so maybe we're seeing tens of billions of years into the past of our universe. So this is a much earlier universe that we're measuring. So you can see that how this, the simulation links up with what we actually measure and how these filaments form through time. So how do we actually see dark matter? If it doesn't emit light, if it doesn't absorb light, how on earth are we going to measure it? So what we use is gravity. And this was described by Einstein, that any mass will affect light, because even though light doesn't have mass, and normally we think that in order for gravity to interact, the particle must have mass. Photons don't have mass, but Einstein revealed to us that gravity isn't really a force in the sense that we think of it. It's actually space-time itself is bending. And so light so a straight line is actually bent when there's gravity involved. So a straight line in space will bend around a mass because that mass bends the space-time. So a photon travels in a straight line. It's just that straight lines aren't straight when you have sources of gravity. So you can think of it kind of like if you had a bowl full of water and you had a few coins inside. You can't really see the water, but if you were to take images of those coins, you know the coins should be round. So when you measure them and they're not round, that must be an interaction of the water with the light that's coming from those coins. And so that's exactly the measurement principle that we use on Euclid. But instead of coins, we have galaxies. Galaxies, we know the shapes that they should be. Every galaxy is different, so that's a challenge compared to the coins, where we know the shape of every coin. And the dark matter is the water that's bending light as it travels to us from these galaxies. So what Euclid is going to do is, so we've got strong lensing. So if you look at, say, a black hole, so if you look here on the left, you can very easily see that these shapes, there's something here that's bending light coming from these galaxies. And this is a large mass. There's a background of galaxies and a large mass in between us and the galaxy, and the light is bending round as it approaches us. And we call that a strong lens, and you often get several images of the same. Here's a distant galaxy, it goes around a large mass, and here's the image that we measure. And for a strong lens, you often see multiple images because the light goes both ways around the object and comes back, and we measure the same object several times in different positions on our camera. For a weak lens, it's much more subtle. And that's what we expect to measure on Euclid is a lot of weak lensing because of this dark matter, which is non-uniformly distributed through the galaxy. So when we look at a distant galaxy, which we should roughly understand what shape it should be, we get a very small change in the shape. So it's either squashed or bent out of shape because of the interaction with light. And by doing a survey across large portions of the sky and hundreds of thousands of galaxies, we can start to form a picture of where there's larger concentrations of dark matter. We get more of this bending than we expect due to measuring lots and lots of galaxies, and we know the average shape of a galaxy and what it should be. And so any difference in that average shape should be due to this light being bent around matter that we don't see. So that was my best attempt at explaining what dark matter, dark energy are and how we're going to measure it. This is just to give you an idea of what the inside of the spacecraft looks like. So you've got the two cameras here, there's VIS and NISP, and a series of mirrors like a telescope focusing light down onto the array. Just to go into the instruments very quickly, there's NISP, which is the near infrared spectrophotometer. That's mostly measuring effects of dark energy. So it's measuring those very distant galaxies and how they are accelerating away from us in order to give us an idea of, is it different in different directions that we look? Information like that is really useful for being able to start modeling this dark energy in our universe. I won't go into baryonic acoustic oscillations. I think that'll take me 5 minutes and then we'll be at the end. So I'll skip over that, but that's something else. It's about very early in the universe. All the matter in the universe was so, there wasn't really space. All the matter was so packed in that sound could travel. And then as the universe expanded, sound could no longer travel because the vacuum became sound couldn't travel because it was too much, like a vacuum where sound can't travel from atom to atom or baryon to baryon. And so what we expect to see are these ripples that were frozen in place. So lots of sound, kind of sound or oscillations were happening in the small universe, and then they suddenly all got locked into place when sound could no longer travel, and that's what NISP will give us some evidence towards the physics behind that as well. This is the instrument we worked on at the OU, the visible imager. This is 36 of these charge coupled devices, and that's the other technology compared to CMOS, which is on JUICE. And this is a very large imaging array. It'll be the second largest in space after Gaia. And one of the main challenges with Euclid, it's not going to Jupiter. It's not going to spend 8 years before it even gets to where it's going. But one of the large challenges is you're measuring these very small changes in galaxy shapes due to weak lensing. And the radiation damage causes much greater changes to the shapes that we measure than the actual effect due to weak lensing. So we need to correct the radiation damage to a much higher degree than we have before on the space mission in order to return good science for as long as possible. So that's where we come in at the Open University, and that's the work that we did. I couldn't resist not throwing this in. So this is the first test image. There was a big press release a couple of weeks ago. The first test image from the VIS instrument, just showing you the wealth of data. This is one image. Here are the 36 CCDs. There's 4 outputs on each CCD, so you see these 4 kind of windows on each one. And when you zoom in just to one of those CCDs, you can see just the completeness of the survey, the breadth of the survey that we're getting here. But even here, you can start to see things which are very interesting. There's some lines here, right? Those are particles that are hitting the camera while it's taking the image, and that particle is depositing charge in the device, which gets measured as light. So you can start to see some of the radiation effects that we need to combat on the mission, and that we did a lot of work in understanding so that we can get the best science out of the mission. So that's a very quick top level view of what these missions are doing. I just want to take 5 minutes to delve into, in a bit more detail, why space radiation is important and what we do at the Open University about it. I've always loved this image on the right. So this is a vacuum chamber at JPL, NASA, many decades ago, and it was an experiment to understand what we call the Van Allen belts around Earth. So because of our magnetic field, particles from the sun get trapped in our magnetic field, and they form these belts. And this was I hope you can see behind the camera. I'm going to move it so I can see it, and then hopefully you'll be able to see it too. You can see an engineer here on the phone looking into one of the portholes on the chamber. So this is a human lab-sized experiment, but they produced a magnetic field on this model of the Earth, and then they injected particles from one side, and you can see how it forms these belts in the same way that we have around the Earth in space. Here's an illustration of kind of what that actually looks like in space. So you've got the magnetic field of Earth, which is kind of uniform in both directions, but because charged particles are coming from the sun, those charged particles press on and push the magnetic field, so you end up with this very lopsided, a very concentrated magnetic field in the front of the Earth facing the sun, and then it extends far beyond the Earth. So these charged particles, they follow these field lines, right? They follow these lines, and so this is what protects us against particles from the sun. And that's part of why we have life on Earth, is because these particles weren't hitting the surface. And things like the aurora borealis are formed when these particles get trapped in these belts. So they do get replenished, and these particles do come through, but then they go along these field lines, and they hit the atmosphere up in the north and the south. And that's the aurora borealis. Is when those particles hit the atmosphere and they glow. But this is when you get outside the magnetic field of the Earth. This is a massive problem for spacecraft, because they're suddenly subject to these particles, and they cause damage to all the materials that are there. They cause damage to the astronauts on the space station and when they go to the moon, and that can cause health problems and all sorts. So it's something that's really important for us to understand. One thing that I like, one example that I always like to give is when the astronauts on the space station close their eyes, they actually see flashes of light, and that's from protons interacting with the fluid in their eyes, causing these flashes. It's kind of the same as the aurora borealis, and they get it in their eyes. So even when they close their eyes, they get these flashes. Don't worry too much about the detail of this. It's just there for people who might be interested. I'll concentrate on one detail here. So this is kind of what a camera looks like if you look as a cross-section through the material. This is all silicon, and there's some metal gates along the top, and there's an oxide that protects the silicon from the metal to make the voltage inside the device. Won't go into any more detail than that. But what can happen in a radiation environment is these particles can pass into the material and they can interact. So our silicon cameras work really well because they've got a almost perfect lattice of silicon. So these silicon atoms are perfectly placed in a regular fashion throughout the whole crystal. Most devices are made from a single crystal of silicon that they grow to this kind of size. So it's a single crystal of silicon without any junctions or anything inside. And what can happen is that proton or particle, if it's got enough energy, it can knock one of these silicon atoms out. And that degrades the quality of the imaging that we can do. So that's really the basics of what 20 years of research at the Open University has been based on is these interactions in silicon and how we can prevent them and how we can correct data once the damaged cameras produce damaged data. So I'll show you a little bit about kind of what that looks like. One really good example are some of the videos that the astronauts on the space station produce for us. They produce loads of videos to engage children and the public and everyone about what it's like to be in space and get them excited about space and entering STEM careers. And this is Chris Hadfield showing what it's like to cut your nails in space. He's got a nail clipper there. But what you can see if you zoom in on kind of the more flat areas of the image, normally the darker areas as well, you can start to see these points of light. And these are pixels that have been damaged by protons that have come into the space station and damaged their handheld cameras. And this is exactly the kind of effect that we measure and try to understand and mitigate when we do our research. Obviously here it's absolutely no problem. There's lots of light coming in, and so these small, slightly brighter pixels really don't affect your image quality. But when you're measuring faraway galaxies, which maybe are quite dim, these can start to give you false positives, make you think that there's light in that pixel when that light isn't actually coming from space, it's coming from damage in the device. And that's the main thing that we try and combat. So this will be a CMOS device because most commercial cameras are CMOS. This is one illustration that I like to wheel out all the time. This was based on work for Hubble. There's a guy called Richard Massey who did lots of radiation correction work before I started my career. And you can see here on the left is the image that you would get from Hubble, a raw image that's untreated. And you can see these radiation effects. Hubble was the only space mission where we were able to replace the cameras. So they got fresh cameras twice in its operational lifetime. And that allowed us to mitigate the radiation damage. But that's obviously completely unfeasible for most space missions and certainly unfeasible for missions to Jupiter. And what you see is this, this horrendous smearing. So what it should look like is on the right, and that's after correction. But the raw images that come down from Hubble have this smearing, and that's again due to these holes in the camera where silicon atoms have been knocked out, and it causes the charge that we measure to be smeared like this. And this is really the image to look at when you want to understand the challenges on Euclid. You're trying to measure the shapes of galaxies, and you've got this huge smearing that's about 100 times worse than the bending you're trying to actually measure. So I think I've got this, and then I'll show you just very quickly what it looks like to do the work that I do. This is a simulation of what Euclid was going to measure before launch. This is the pure galaxies that went in. So this is the sky that we're observing. And after about 5 years in space, the images that we get actually look a lot more like this. And this is the prediction. So we haven't really gone into detail about how these devices operate. And so I don't think we'll go into detail about why You see less smearing on the left here to the right, but that's just an effect due to the type of sensor that Euclid's using. But you can see these lines, the lines that we saw in the actual Euclid image. And those are particles hitting the device while the camera's taking an image, because it takes 90 seconds to take an image rather than instantaneous. So there's lots of time for these particles to deposit light where it's not coming from galaxies. And then you see this smearing, and the smearing really, if you take a galaxy, if you're trying to measure the shape of that galaxy, it's going to be completely distorted by all these trails that are going off to the right. And so the work that we've probably spent 15 years on Euclid trying to understand the damage that it's going to experience in space. And it really is, in a couple of years' time, as the radiation builds up in the sensor, it'll be a real test of the work that we've done here, to see if we can correct this data so that it's as good as launch day. So we get the best possible science for the longest possible time. And that's what our work is all about. I'm not going to spend too long on this, but this is kind of just give you an idea of what it actually looks like, what we actually do. So on the right here, so on the left, these are two Euclid type devices mounted on a cold head. So some wires and things to transfer signals, and it's on a copper bench because the copper conducts heat well, and we want to cool the devices because in space they're going to be about minus 120 Celsius, so we need to cool it to that in the lab. And we operate those sensors in a vacuum chamber. Obviously, to cool them, we need to get rid of any air because air will have moisture in, and as soon as you cool it, you get water on the electronics, which is a no-go. And these chambers are designed so that we can take them to facilities and irradiate them with protons. So the bulk of our work is we measure how good the cameras are at making images, and then we take them to a beamline, we hit them with protons, electrons, gamma rays, things that we're concerned about for the specific mission. And then we bring them back to the lab and we measure how that image has changed, how the quality of the image has changed. And those measurements inform our theory of what we think is going on inside the silicon. And then that theory goes into models so that we can come up with the best way to treat data on board spacecraft where we can't necessarily measure what dose has hit the device, for example. So that's kind of the chain of operations of what we do. I'll leave you with this. It's not the latest indie album cover. It's a selfie of myself and two of my colleagues at a beamline. So on the left here is our chamber with the devices in, and the protons come down this beam. So there's a big accelerator, and they have different rooms where they pull off the protons from the main line and pull them into a room, and we can do testing. So they do lots of kind of proton testing at this specific beamline. Just to give you an idea of what it's like, it's normally very cold and it's like a dark cellars. All the bricks in the wall are contain lead and things, so it's nice and safe. And there's these procedures for locking off the chamber when you want to do your irradiation and things. That's just give you an idea of what it actually looks like to be doing this. So I think it's been a completely crazy quick tour, and I wish I could spend longer talking about all of them with you. But I hope it's given you a taste of the science that we'll be able to accomplish with these two missions. Euclid is doing its calibration at the moment. JUICE is on its way to Jupiter. The challenge with JUICE is that it's going to get irradiated for 8 years before we even start doing measurements. So all of that radiation damage will be building up for 8 years. And then we have to do science with an already damaged detector. And that's why we chose this new sensor technology, because it might just give us that edge in reducing radiation damage. And really the key is, us here at the OU, we help the space mission teams to get the best out of their cameras for as long as possible in space. Most space missions generally operate for about 5 years, and the main reason for that isn't lack of propellant, lack of cooling. It's about the science at the end of 5 years is not as good as at launch, and so it doesn't make sense to operate it for any longer because the science is just not good enough. And so the understanding that we add here at the OU allows scientists to push those missions beyond the 5-year nominal lifetime. And in the case of something like Gaia, it's been operating for twice its predicted life. and we've gathered such a greater wealth of information because of the work that we do here. So thank you so much for listening. I'll leave you with this is a picture of the entire sky and the size of the Euclid camera on top of that sky. So you can see how many images we will have to take to cover the entire sky. And we'll do that many times over the mission lifetime. Thank you. I'd love to answer some questions if we have time.
That was absolutely brilliant, Ben. Thank you so much. It was a brilliant whistle-stop tour of some of the amazing missions that the CEI have been involved with, and you personally. We do have some questions. We don't have much time, but I think if we sort of do a sort of quick answers to them. I'm going to start off with a question from Alicia. Is there anything planned for JUICE research-wise for the 8 years that it is travelling to reach Jupiter before it actually reaches there?
That's an interesting question. I think, JUICE has done a lot of its kind of calibration phase work. So it's, you might have seen in the news, there was some problems with getting one of the antennas to deploy, and they kind of had to jiggle it free in order to deploy properly. I think there are some instruments like the radiation monitoring and magnetic field instruments that can take measurements of space as it goes along. For our instrument, for the camera, we're really trying to hibernate it until we get to Jupiter to try and protect it from some of these radiation effects, because it does get more damaged while it's operating. So we're going to turn on as we approach Jupiter, or if we're going to do flybys of Venus and Mars. So I think there are some plans to turn on and take some flyby pictures, and that's more to do with getting the public excited about the mission while we're waiting for 8 years, more than doing proper science with the instrument. But as we approach Jupiter, we'll be able to get nice and close and take those high-res images that will be real science.
Brilliant. I've got a question here from Germany, what I think will come into sort of annealing. It sounds like a lot of the work is to correct noisy data. Are there any methods for self-healing cameras, so to correct it in the camera itself?
Super, great question. Yeah, so obviously you've got a few things you can do. You can shield the camera better so less radiation hits it, right? So lots of work goes on to try and minimize the amount of radiation hitting the camera in the first place. The problem is that you want photons to hit the camera, so there's always going to be a way for protons and other particles to get in, and the high energy ones will just pass through any shielding that you want, and gamma rays as well, unless you put something really heavy on, which you don't want to do when you're spending lots of money on fuel getting something into space. So there's obviously Hubble, which was the very lucky one that we got to actually change the cameras to put fresh ones in. So that's a really good example. What they've done on earlier space missions, where we had a bit less understanding maybe, is that those kind of where the silicon is disrupted because of an atom's been knocked out, that's actually kind of frozen in place because you're at a cold temperature. And what you can do is actually, if you heat up the sensor to, say, room temperature, there's a lot more energy in that lattice, and that vacancy that was previously frozen into the lattice can actually move around, and so that vacancy moves to an area of the device where it doesn't affect your signal anymore. So previously missions have had these heating cycles where they've tried to heal the array through temperature. Now, some of our understanding in the last decade has actually shown that perhaps that isn't the best way to heal the sensor, and it depends a lot on the mission and how you're operating the device as to whether that is a good technique to try on your space mission. So we've actually advanced that understanding here at the OU over the past decade. You actually find that for some cases it will make the effects worse rather than better, because those vacancies, those gaps in the silicon, were frozen in a way that didn't affect you so much, and if you actually put that energy, it might actually turn into a different kind of trap that would affect your image more. So I hope that's a really detailed question, and I could probably talk for an hour on that exact topic. I hope that gave you a taste of the answer. Yeah.
Which then is going to be possibly a question with an answer to the next question. So for brevity for this one, if we do this one and then one more,
Okay.
this is sort of the age-old argument. What factors were behind the decision to use CCD technology for Euclid and CMOS for JUICE? So,
yeah, so CCDs are what we would say mature technology, right? So they've what traditionally have been used for space, and the advantage with CCD technology is that there's only one output or a very small number of outputs on the device, and you actually move your image to the output in order to read it. And that's contrast with CMOS, where there's an output in every pixel. And the breakthrough for using CMOS in precision applications is our manufacturing has gotten so good that those outputs can be uniform. That was one of the big challenges for CMOS. So with CCD, you only have one output. So that output is what it is, and you don't need to worry about calibrating it. So that's kind of, the pros and cons. For JUICE, we chose CMOS because you're not transferring the charge, you don't actually get that smearing that we talked about. That smearing is a big problem for CCDs, and you don't get it in CMOS. So CMOS was, maybe a decade ago, when I studied this for my PhD, CMOS was believed to be the choice for radiation harsh applications because you wouldn't get this smearing. Now, in my PhD and subsequent work, we've discovered that because you have a lot more electronics in each pixel, there's a lot of different radiation effects. So it really comes to a trade-off of what you're trying to measure and which effects are the ones which, do you care about CMOS type effects or CCD type effects? So I think CCDs were chosen for Euclid really because the work that begun for Euclid was in the CCD era, and they were the precision sensor of choice, and they're still very good for certain applications, and the sensor of choice for certain applications. I don't think CMOS is going to replace CCDs completely. So I think it really did come down to that, and we've done a lot of work to understand the radiation damage in CCDs, and the correction we have to do for Euclid is so beyond, I think it's beyond really our understanding of radiation damage in CMOS, whereas something like JUICE, you're taking images of a bright surface of a planet, so that radiation damage doesn't affect you so much. So you don't need to understand and correct it to quite the level that we do for Euclid. Euclid really is the most radiation damage affected measurements that we've ever tried to make. It's that heritage that we have of understanding how to use it that I think fed into the Euclid decision to use CCDs. Sorry, that wasn't a quick answer.
Sorry, I'm going to do one very quick one to end, if that's okay. So I'm realising we're running out of time. Do you have any advice for OU students about where to look for involvement in real projects like this? Or, sort of as a company, what should they do to prepare themselves for being involved in this kind of projects in the future?
In my experience of working with our undergrads and our master's students and PhD students and colleagues, I always concentrate a lot on what separates you from other people who might be looking at the same kind of position that you're passionate about. And for me, that comes down to skills a lot. I think it's really important, especially these days, for students to spend the time to really concentrate on maybe the less obvious skills that they're developing in their modules. And the OU concentrates a lot on this. We provide Python teaching from a very early level in our physics curriculum. And even on my master's course, we concentrate a lot on assimilating information from external sources rather than just giving you material to study. You need to go away and read space agency reports and papers from academics. And we spend a lot of time working on things like team working and how to build a team cohesively and work in a team and be confident to speak your voice in a team. It's hard to be able to give our students opportunities to actually get involved with the kind of stuff we do. But I think if they concentrate on building the skills which set them apart and make them employable and attractive, then they'll be in a good position if they wanted to move into, say, a master's project or a PhD project in this area. It's really those skills that can set them apart.
Sorry, I was just saying, brilliant. I've just added into the chat as well the link for the torrent PhDs that are currently live with the CEI as well. We both did our PhDs with the CEI, so we've got a lot of experience with them, and I think the next round is February.
I feel like they're going to be advertised in February, yeah. And I know we've got at least 3 in the pipeline of projects that we have that we want people to, the next generation. And this is something I talk to as well, is I'm getting old now, or I feel like I'm getting old anyway. And these space missions take 50, Euclid we've been working on for 15 years, JUICE we've been working on for 10 years, and it's going to take 8 years before it gets there, and then the data is going to come down, and we need the next generation to come and look at the data that we've sent instruments up to take, and plan the next generation of missions for the next generation of scientists that come through. So there's lots of opportunity to get involved, there's lots of work, and space is one of the areas that's growing at the moment. So it's a really exciting time to get involved.
Brilliant. And I think that's probably a brilliant place to stop for this session. Thank you so much to Ben for a really brilliant and really interesting talk, and thank you all for joining us.
Thanks everyone, take care.